is Mr. Bernie Thompson. Thank you, Bernie. Thank you, everyone.
Good afternoon. I sure appreciate each and every one of you coming out. It's great. I know how hard it is to come out on a weekend and do training, so we'll try to make this worth your time. I mean, obviously, I think it's already worth your time. My esteemed colleagues earlier, Scott Brown, Wayne Colonna, Peter Meyer, have done just a wonderful job. Hopefully, I'll be able to do as well as they've done. Today, we're going to do a class that's going to involve fuel injection. And I want to cover the basics of fuel injection so we all get a better understanding of how the system really is in function, not how we might think it is. Many mechanics have some misunderstandings on the system. We're going to try to clear some of these up. So we'll go through a base understanding, and then we're going to go to some case studies. We've got lots of really good case studies. The one thing that this class is about is not case studies. If you guys came and you see some case study and you're going to try to make this direct link to the case study and it's going to help you in your bay, that might happen. But if that's the case, I have not done my job well. My job today is to give you ideas. This is ideas. This is things that you use. This is ways that you're going to think about looking at systems to where you can rapidly diagnose a car. We want to be fast with our diagnostics. We can't afford the time that it takes. So my name is Bernie Thompson. Some of you know me, some of you don't. So I own Automotive Test Solutions with my business partner, Neil Peterson. Together, we've designed a quite unique set of tools, one of which we'll see some of today. But we make 5-gas analyzers, ignition analyzers, oscilloscopes, pressure transducers, scan tools, leak detection equipment. So we really make a wide variety of equipment for the automotive technician to use in a service bay. During the event of each one of these tools, and when you're looking at how things operate, I get a better understanding myself. And so that's sort of what I'm here to do today. I'm here to help you guys with some of the understandings that I've gained because I have access to time in order to engineer the equipment. And you really look at it a little bit differently when you really start to engineer the equipment. So let's just take a real quick look at a couple of fuel trim sets. Here's one fuel trim set that obviously is going from 30 at the bottom to 5 at the top or 12. So it's adding a lot of fuel at the bottom. That means at low loads, and we'll cover these in some depth today. But right now, all I would really know about this car is I'm adding fuel. Isn't that correct? Couldn't that be a lot of different things? Is that a fuel pump? Well, I don't know. Is that fuel pressure? I'm not sure. Is that a mass air sensor? Again, I'm not really sure. The only thing I know is that I'm adding fuel. Is that a computer problem? Well, we're adding fuel. Here's another one. We're taking away 14% at the bottom, and at the top we're adding 36%. So again, I'm not really sure. I could believe that this type of table would give me an indication of where my problem might be. But to be sure, I'm not sure other than I'm adding fuel really under load. Here's another one. I'm going 5 at the bottom and I'm adding 14, 15 at the top. So under load I have to add more fuel. What's that? A plug fuel filter? Well, I'm not really sure, right? All I know is I'm adding fuel. Here's one where I'm 5, 8 at the bottom and I'm going 48 at the top. What's wrong? Oh, I'm really not sure. Here's one where I'm taking away 25 at the bottom, and I'm only taking away 18 or so at the top. What's wrong? I'm taking away fuel, right? Why am I taking away fuel? Many of us don't quite understand what trim is. So what we really need to do is we need to get into the idea of what it is and how it works. So we're going to cover these towards the end of the class if I don't run out of time. But regardless if we get back to these or not, we're going to have a really good understanding of what I'm talking about. In the last 100 years, automobiles have had a major transformation. The new electrification, such as in the Volt, these cars are very sophisticated. This still uses an ICE engine, internal combustion engine, but it also has a powertrain that's very unique with an electric machine, or an electric motor helps propel the engine. The electronic systems, they've just become very complicated, and they're overwhelming to a lot of technicians. You know, these cars, let's not even talk about a Volt. Let's talk about the cars that are in your bay every day. They have way more power than the space shuttle. So the space shuttle has less processing power than the car that pulled into your day yesterday. Your car that pulled into your bay. What we really need is a better way to find the problems. You know, everyone's afraid to do these diagnostic cars. I lose money in diagnostics. That's what I always hear. But you know, in order to make the money on the easy stuff, the brakes, the belts, the oil changes, where my shop used to make the money, I got to do the harder cars. Because if I can't fix the harder cars, you know where they go? To the guy who could fix them. And then all my gravy's down the road. I don't get the money. So the idea is where do we fail with our diagnosis? Well, 80% of the shops, or 80% of the cars that are hard are pretty easy, right? They're moderate. They're not too difficult for you. 13% can be real difficult. 5% is extremely difficult. And 2% might not be able to be fixed by the shop. You might have to call in a mobile technician, or there's many different ways, but you might not fix those cars. But the bottom line is whether I can fix the 2% or not. What about the 13 and the 5, the 18, or the total 20%? Do you realize that you're wasting all the money that you made on that 80% on this 10% of cars? Because these 10%, I can just work and work and work on the car, but I don't get paid for it. So what I want to share with you is a way to where we're not going to do this. We're going to actually make money doing drivability problems, because that is what's available for us. We just need some techniques. So in order to diagnose fuel injection, you know, and you want to do this fast, and you want to be accurate. We don't want to hang parts. We got to stop thinking about these systems the way that most technicians do. And I didn't tell you one thing. I'm a mobile technician. So during the week, several days a week, I go out and I service 220 shops in my area. So that includes dealerships, body shops, and just basic repair shops. I see where guys make their mistakes, and I want to try to help all of us to where we don't do that anymore, where we can actually be quicker and more accurate. So fuel injection, the name fuel, is obviously what this is about, right? It's got to be. It's fuel injection. So what does it do? The fuel injection pressurizes the fuel rail, and the fuel rail under pressure is connected to the injectors, and the injectors open up for a metered amount of time and deliver fuel to the engine. So I'm going to have to do something in order to figure out the metering. But we know that we're going to release fuel into the engine. The fuel injection can be defined into two basic types, mechanical and electronic, right? Because we had mechanical, we have it on diesel, and we also have mechanical on many of the European models. I mean, Porsche used mechanical for years. So there is different types of this, but what we're really interested in is we want to look at the electronic system. The electronic system is one that would be put with a spark ignition engine. We don't want to look at the electronic style that would be on compression ignitions. We're going to look at the mainly what gasoline cars would include. Some early fuel injections had no code capability. We all remember that. I remember when I started to work on my very first VWs, right? And when these cars have any kind of a problem, they don't recover from it, right? So if I've got a cylinder head temperature sensor on one of these early air-cooled engines, it would take the whole system down. It couldn't overcome it because there's no feedback. We only have feed forward in these systems. But whether I had a code on early systems or I don't have a code in early systems, because many of the cars, even the Asian models, right up until 96, some of them had no codes, right? You look at some of the Mitsubishis that are in 94, 95, I didn't have really any way to troubleshoot them as far as them helping me. But now, we're sophisticated, we have all this help. These computers are going to really do a good job for us. They're going to help us. They're going to give us DTCs, right? So now on these later ones, it's a breeze, right? Because I got codes. Well, that might not necessarily be true. So let's look at how accurate this is. This is a system that we set up in order to backwards engineer the communication systems to the modules. So I go down to the junkyard and I get a computer out of the junkyard. If you notice, the wires on here are powers, grounds, and communication lines only. There is no additional wiring from my box into the computer. Does everybody see that? So if you look, we see the wires here. These are only powers, grounds, and communication lines. That's it. I plug into this, and then I'm using my scan tool, and we figure out the right coding sequence to talk to it, make the handshakes, and get the communications from the module. This is what the DTC said on this. There's not any. There's not one wire connected to that module. What do you guys think? Is this going to help me? You realize that we have to go through certain enabling criteria in order to set a code. In other words, we got to have it under the right conditions. Conditions, that means that it's like a laboratory. We don't do testing in a laboratory without controlling the variables. The engineers don't want to do testing on your car until they're controlling the right variables. So until the right variables are enabled, I'm not going to run the test to tell you that all the wires are open even, right? And that's something that you might not have thought, because the comprehensive component monitors, right? Aren't they supposed to find these wiring problems? Well, do I have any wires on that computer? Powers and grounds, but I don't see anything. What about the open MAF sensor? Okay, so let's look at a later one. So here's a CAN off of a 2006 Ford. Okay, I actually set some codes now, so that's really good. I want you to take notice of these codes. They're all for drive-by-wire systems. Drive-by-wire can kill people, so they're more interested in setting them. But what about the throttle actuator control forced idle, throttle actuator forced limited RPM? Do you think that that was running? Did we have an RPM signal going into this? How come it set something that it can't be? There can't be forced idle. The thing can't idle. It's not connected to a motor to idle. You got to understand how DTCs are written. DTCs are written by an individual who is trying to look at the data the best way they can. A computer is a blank slate. It cannot do anything without the proper steps written in it. Every program has a series of steps that have to be carried out in order to set a DTC. And that's going to be who's programming it and how those are going to be set. Each system and each manufacturer might be different, but as we can see, codes don't always work, right? So since codes don't always work, what am I to do? I've got a problem with my car and I need to fix it. So what we need to do is take the DTC as a bit of data, but not the only data. When I go to shops, many times the shop would have fixed the car if they could have just stopped looking at the code. They get so focused on this code. This is what's wrong with the car because the computer says it's what's wrong. But we just saw that a computer not even connected to an engine says we forced idle. We didn't, and we didn't limit the RPM because there was no limiting factor. We don't have RPM. So we got to start to understand that codes aren't going to help you, but they are going to give you an indication. Doesn't mean that that's what's wrong. So when you're working on a car, the code is just something, another data piece, another PID of data, take it. Doesn't mean it's what's wrong with the vehicle. Fuel injection is part of the engine's control system. This regulates the air if it's drive-by-wire, right? You have to have drive-by-wire in order for it to regulate the air. Fuel, spark, timing, and we're going to have some other things, but we're always trying to put an outcome for the torque. The driver intent, or the driver, is going to determine what he's asking for, right? From the microprocessor. In order to do this, the driver is going to push on the accelerator pedal. But if I push on a pedal alone, did I give any information to the PCM? It doesn't know anything. The driver knows that if I push on the throttle pedal, a Bowden cable in the old days went over to a throttle blade connected to a carburetor. And as this throttle blade opened, Due to physical events, I could fuel the engine through the carburetor. Well, we've got to carry out that same task of delivering fuel, and we've got to know what driver intent is. We're going to do this with sensors. So we're going to do a throttle position sensor, a TPS. The TPS now becomes the interface between the driver intent, and the PCM. This is a major sensor for every manufacturer. It is the piece that interfaces you to the computer. When you have your PC, you use a mouse. So you wiggle a mouse around and you click on the mouse. In order to be able to get the PCM to do anything for you, you've got to give it requests. It's got to know how to carry out the program task that you're asking of it. In order for this to happen, we're going to watch the TPS not only for what I'm doing, am I at idle, am I at light cruise, am I wide open, but also how rapidly the throttle opens so I can give acceleration enrichment. Now when we go to drive-by-wire, we're going to do a very similar sensor for driver intent. Again, an interface. It's like your mouse between, or your keyboard. It has to be interfaced to the processor to understand what the driver is asking for. This will be the accelerator pedal position sensor, or the APPS sensor, on drive-by-wire systems. The APPS is a request. It doesn't mean the throttle is going to open. It's going to mean that I'm asking it to do something for me. This is a request, and the microprocessor will look at this data and determine the best way to give you the torque production from the engine that you're asking for. Sensors take a physical quantity and convert it into an electrical voltage. All sensors. So regardless of what this is, sensor-wise, we're really taking something from the physical world, and we need to be able to change it into an electrical value that we therefore need to change to a binary code set so a microprocessor can deal with this. So sensors, if I got a crank sensor, I'm really watching the physical movement of the crank, right? And if I watch the physical movement of the cam, it gives me where the cam position is. When I put the cam and the crank signals together, it gives me crank angle space. Crank angle space is needed so I can control the engine. I have 4 strokes. 2 of those strokes are going up and 2 of those strokes are going down. Now with a crank sensor alone, I would be able to figure out crank angle degree, but I can't figure out crank angle space without a cam. I need to know if the intake valve is open, so as the piston comes down, that's an intake stroke. I need to know that to be able to give the proper timing to the injection. On one stroke, when it comes up on compression, or exhaust, wouldn't I need to know that? If it's on compression, I need to fire a coil at the right time so I can start the fuel to burn. If I'm dealing with something like manifold absolute pressure, we're dealing with a pressure value that's in the intake manifold. Again, it's a physical quantity that we're measuring, and we're turning these physical quantities into voltage. The voltage is going to see, or the computer is going to see the voltage through something called an analog to digital converter. An analog to digital converter, an A&D, takes voltage as an input, and then it puts out a binary number set, zeros and ones. No computer sees voltage, no computer sees any current, they see binary. So all computers deal with binary code setting. So if I wanted to see, let's say a TPS at idle, we'll say is about 0.5 volts, and then as I open the throttle up close to wide open, I'm going to be at 4 volts. So this would be an indication. You can see that the number sequence at the bottom is changing. These are actual numbers that would indicate that voltage if we had a real A to D converter. But the binary code set's really what we're looking at. So the driver intent in turn opens the throttle blade, allowing more air to enter into the engine, whether it be a Bowden cable attached to the throttle pedal or whether it be actuated by a motor. One way or another, the end result is we're trying to open the throttle restriction up so we let more air go in. The more air that goes in, the more fuel we can mix with it, and the higher fuel concentrations will produce a higher torque value from the engine. So what really is the fuel injection doing? It's calculating the air entering the engine, right? Because it'd have to. We have to know the air weight before we can do anything. We're commanding the injector on time, the injector sequence, the timing of the spark, and the spark sequence. And we got other functions, don't we? Cam phasing, EGR, if it has an EGR. But we have other systems as well, purging the canister for the evaporative emissions. So there's many different things that we're going to have to take into account other than the basic commands. But in order for any of this stuff to happen, we need to deal with one major factor first. We think about fuel injection about being about fuel. It's fuel injection. But really, what we need to start to think about is the fuel injection is about the air. It has very little to do with the fuel. When we can get past this mindset that it's about the fuel, and we can wrap our head around the fuel injection is really about the air, we can start to fix cars unbelievably rapidly. What I want to show you today is a methodology that I've used for years and years and years, where you can drive the car around the block and you know what's wrong with it. And we're not exaggerating. We want to prove this. It's about the air. The first outcome that has to be done is an air weight measurement. In order to do cam phasing, in order to do EGR functionality, in order to do fuel delivery, weight delivery, I have to know the weight of air that entered the engine and what the load against the motor is. So the air becomes the big factor. If we start to think outside the box, we can see it's the air. The fuel is a known quantity. The air is an unknown quantity. Why do I say that? Well, let's take a look at what a fuel injector is. The fuel injector, the flow rate is known, right? If I have a known orifice size in this injector, and I'm putting pressure against it, in order to increase the volume output from this injector, I either have to increase the pressure or I got to have a bigger hole size. Does that make sense? This is just a flow. If I have a bigger hole, I can have less pressure and I can have the same flow. If I have a smaller hole, I have to have more pressure to obtain the same flow. So really, injectors, they're based on a restrictive orifice size against the working pressure of the system. This orifice size is rated as what's known as injector slope. Injectors are bought and sold as far as injector slope. Injector slope really means it's telling you how much weight the injector can deliver. So if I had this injector and I had it just flat open, it was just flowing, and I had a working pressure against it, and I had a bucket underneath it, and I caught the amount of fuel in 1 hour, we could rate that injector. So if we had a 46 pound per hour injector, this would basically give you an idea. I don't want anyone here to get all caught up in any of this math. I want you to get caught up in the idea of what I'm talking about. If I had 46 pounds per hour, I would have 7.36 gallons of gasoline. 1 gallon of gasoline is 6.25 pounds at 70 degrees Fahrenheit. 1 pound would contain 3785 cc's. 6.25 pounds times 3785 is 23,656 cc's per gallon. But I have 7.36, so I'd have to multiply that. I have 174 cc's in an hour. So 46 pounds by that would be 174 cc's in an hour, right? That makes sense. But now I need to get this down to seconds. There's 60 minutes in an hour, 60 seconds to a minute. You do the math, you got 3,600 seconds per hour. So now you take the 36, divide it into the 174, I would have 46.36 cc's per second. I have 100 milliseconds in a second, right? So I'd have 48.36 cc's divided by the 1,000 milliseconds. I'd have 0.0483 cc's per millisecond. That's a known factor, right? I don't have to deviate from that. We're all going to become calibration engineers today. I forgot to tell you that. But you really are. We don't need to know the math, but we need to know the idea. The idea is if I take a fixed injector that somebody has engineered, it gives me a fixed amount of fuel delivery that I can quantitate. I absolutely know that if I open this injector up for 5 milliseconds or 20 milliseconds, I can depend on what? The fuel weight that's delivered. It is a known factor. Do you see why I say the fuel is a known factor now? Now the air is the unknown factor. I have no idea how much air is entering the motor. So I'm going to have to calculate the air weight. Now we do the air weight by 2 different types of systems commonly. But there's actually one other system that we need to calculate. And all this air weight is going to be grams per second. That's really what our scan tools display that out, so that's what we're going to be talking about. So there's several different ways in order to equate the air's weight that's moving into a system. Each one is different. We'll look at a couple. Speed density, that's a method of measuring the vacuum in the manifold in order to calculate the air weight. This is an indirect method. It doesn't mean that that much air went into the system. We really need to understand this. So I have speed density, and speed density, when the throttle blade or the throttle valve is closed, the engine, with the piston moving down, creates a low pressure area. Atmosphere is trying to push in, but it can't because there's a restriction in the way of the throttle valve. So I make a negative pressure, I make vacuum in the induction system. This vacuum in the induction system is what I'm going to use to figure out the load against the motor. As I open the throttle up, the atmosphere will rush into the intake because high pressure always goes to a low pressure. The high pressure rushing into the low pressure eventually will equalize itself when there's no more restriction in the way. So if I open the throttle, wide open throttle, on anyone's car, you need to be within 3 kPa of atmosphere. So if I was here, let's say we're about a sea level, that would be 101 kPa. That means that if I open the throttle wide open, I need to be somewhere around 100 kPa, right? Well, if I'm 95 kPa, you still have a restriction. You have a plugged rat's nest in your intake, or you got a plugged air filter. You have some type of a restriction. So under wide open throttle, the blade no longer is a restriction. So the atmospheric pressure should equalize to the manifold pressure. Does that make sense to everyone? As I close the throttle, I will start to make more resistance. This resistance, as the piston is moving down, will create a negative pressure. So I can make an equation based off of just a few facts that I know. If I know the barometric pressure, and I know the air temperature, and I know the RPM, and obviously we know the liter size because we're programming it, we can write a real basic equation that will say that the vacuum equates to a weight of air entering the motor. Now this is inferred because I'm constantly going to look up tables. When we calibrate engines, we build an engine map. This engine map is called a volumetric efficiency map when you calibrate stuff. And it's really saying what the weight of air is at a certain voltage output from my sensor, right? So the sensor is reading vacuum, and the vacuum is going to be converted by the sensor to a voltage. The voltage is then converted into a transfer table. The table is going to take voltage and equate it to how much air it is going in by tables. So if I have a certain vacuum, which would be a voltage, the computer would go in and look at the load and the RPM at this target point, and it would be able to equate at that point X amount of air weight is entering the engine. So anytime you're using speed density, it's constantly a battle of going back and forth and back and forth. Lots of looking up on different charts and trying to figure out what my weight is. This is all done in calibration. The manifold absolute pressure sensor is going to be made with a diaphragm, and I've got an absolute vacuum under it, right? That's why it's absolute, because it has vacuum. As I change the pressure on top, I flex this diaphragm. This diaphragm will change these resistances on the bridge. This is a Wheatstone bridge, and the Wheatstone bridge is going to make a change that will be amplified out, and that's what we see as our signal. Very straightforward sensor. Mass air is a direct way of measuring the air. Now, one thing I want to make a point of right now is, if you noticed, this map sensor, a map sensor like this, is always going to be behind the throttle blade because it's reading vacuum, right? The mass air is always in front of the throttle blade. Why do I say this? Do you guys work on Subarus? They have a speed density system with a map, and it's behind the throttle blade. When it comes up on your scan tool, it is called a mass airflow sensor. When you look at a wiring diagram, it is called a mass airflow sensor. Is it a mass airflow system? It is not. It is a speed density system. If the sensor's behind the throttle blade, it is speed density. If it is in front of the throttle blade, it is direct measurement. And I'm going to explain this because you've got to know which system you're working on because they work quite differently with fuel trims. So this particular sensor is going to always be in front of the throttle blade because I need laminar airflow. I need the airflow to be unified across it. I don't want turbulent air. Any turbulent air will be a misreading because the air could hit the sensor several different times and create an air measurement that would not be correct. Again, I'm going to use a Wheatstone bridge. This is the old style, which is the Bosch style. It has a platinum wire in it. The platinum wire is 2.7 thousandths in diameter. The platinum wire will be heated. Now, it's heated up above the ambient air temperature because temperature always goes from the hotter element to a colder element, right? Now, if the engine runs at 200 to 300 degrees, that means that that wire's got to be way hotter than the engine so it can give its heat up, right? So this sensor is going to run about 425 degrees Fahrenheit, along with most of the other type of sensors like this. Whether it's a hot wire or a hot film sensor, they're all heated. And they got to be heated above the working temperature so they can give heat up. We all already understand the principle of this sensor. It works off convection. Convection is what we call wind chill. So if we go outside and it's 30 degrees and I'm just in a shirt and there's no wind, sun shines, boy, I feel okay, don't I? But if it's blowing 5 miles an hour, I'm cooler. If it's blowing 30 miles an hour, I'm going to freeze to death. The temperature never changed. What changed is the amount of air coming in contact with your body or your skin. When air comes in contact, being a good conductor of heat, it takes heat and it carries it away from my body. Every molecule of air that comes in contact with this hot wire is going to take thermal energy or heat away from the wire. A bridge function, which is the Wheatstone bridge, is going to try to keep this wire at a set temperature, let's say 425 degrees. So if I am at 425 degrees, and now I start to move air across the wire, the air is going to carry heat from the wire. That's going to reduce the heat in the wire, which means that the resistance of the wire goes down. Now, as resistance goes down, current goes up, right? So really what we've got is something that works proportionally. The more air molecules that hit this wire, it carries more heat away from it. The resistance of the wire, being platinum, changes dramatically. The bridge tries to keep the temperature the same, so more current goes up. So with more air, I have an equal amount of current. So if I watch the current in the wire, it's proportional to the airflow. It's actually referred to as the King's formula, semi-empirical King's formula is what really makes this wire work. Has to do with velocities, but it's really, you got to realize that this wire is actually reading molecules. So it knows exact air weight, and it's a direct measurement. I don't have to go necessarily and keep looking up a table, but we are going to look up something, and that's called a transfer function. In transfer functions in the processor, I have to take a voltage. Now, if this sensor produces a voltage, what does that really mean? It's got a voltage, but that didn't really tell me how many grams of air it flowed, did it? It's a voltage. In order to be able to transfer that voltage into an actual gram weight of air, the engineers take an engine and they take the heads, they take the entire intake manifold with all the structures all the way out to the air filter. They assemble it on a flow bench. They flow a known quantity of air. A flow bench is a very accurate instrument for measuring air weight. They flow air through those heads and through that sensor. Now, when they know the exact target of how much air is flowing, they look at the voltage, right? So we'll just make an example. I got 2 volts. We'll say we have 100 grams of air. So if I had 100 grams of air, I'd go write that to a table. So it would say, at this voltage is equal to this much air. And I would write a transfer function table that's transferring the function of voltage to gram weight of air. Now, all computers have transfer functions in them. You've got to realize that the fuel pressure sensors on your rails, that is a voltage. It must be converted so the computer knows it. And the conversion charts have to be right for the sensor for the correct voltage. Does that make sense? So when you put a mass air sensor on the car and you don't ever read the little tag that comes in it and it says it needs to be reprogrammed, really what you're doing is you're changing the transfer function in that computer. And some of these computers might have 5 transfer function tables that are broken up over different load and different RPMs. The idea is there's something in here, a program's going to change this thing, and we got to be aware that if we need to reprogram it, that we do so. Once the total air entering the engine has been weighed, we need to figure out how much went to each cylinder. Now, that's going to be the same no matter whether I have speed density or I have a direct air measurement. The one thing that I've got to know isn't the overall air weight that came into the motor. Does that really matter? This isn't a TBI car. We're not giving fuel through something that would resemble a carburation system. We are giving port injection or possibly direct injection, where we are fueling one cylinder. Well, in order to fuel one cylinder, I have to know the cylinder weight of air so I can deliver the appropriate weight of fuel, right? Now, one of the things that we need to understand is that's one thing we need to do, but let's not get away right now from speed density and direct measurement, mass airflow. You have to know which system you are on. That's why I made a point that some cars sort of don't tell you right, and you've got to be able to be an investigator. You've got to go and look and see what system you've got. What are we working on? Why would that be so important? Okay, if I have an air leak, and I've got a direct measurement, a mass air, and I pull a hose off the motor. Now, air went into the engine, didn't it? The air went in, but did the mass air sensor weigh it? There was no weight measurement made by this sensor. So I underread the amount of air. Does everyone see that? I did not weigh the right amount of air. I underweighed it. Now, in order to correct that problem, and we're going to see how we correct this shortly with trim, but we're going to trim it, and we're going to have to add fuel to the system, right, to make up for that. So the trims would be adding fuel for a vacuum leak on a direct measurement. Does that make sense? On a speed density system, if I pull a hose off, didn't the air go into the engine? So it changed the vacuum? So it really did, the air really got in there and the vacuum really changed? You'll have no trim. So a vacuum leak on a speed density system isn't going to trim you. A vacuum leak on a direct method is going to trim you. If I have an exhaust gas recirculation valve, and this exhaust valve opens up and it dumps inert gas in to displace the incoming air, right? Because isn't that what EGR does? It displaces the air in the intake manifold. Now, if I displace the air on a direct method, which would be a mass airflow sensor, the air was read right, isn't it? Because I took it from the exhaust and I put it back into the intake, so all the air that went into the motor was still read correctly. There's no trim. I will not trim for an EGR valve that's open because I still read the right amount of air, I delivered the right amount of fuel, I don't got to fix it. Does that make sense to everyone? Okay. On a speed density system, if I open up an EGR valve and I displace the volume that's in the manifold, don't I drop my vacuum? Well, if I drop my vacuum, when I lose vacuum, the more vacuum I have in the intake manifold, the program says I have less volume of air because the throttle blade is closed. As that pressure rises closer to atmosphere, I start to have less vacuum in there. Doesn't that say that I'm under load? I open the throttle blade so more air is going in there? So if I opened up an EGR valve and I displaced a certain amount of volume in the manifold, it would lower the vacuum, wouldn't it? Wouldn't I go to my lookup table and it would say that I'm under load to add fuel? Did I have more air coming in? Do you see how that's an inferred method, not a direct method? The two will work quite differently. So on anything to do with air readings, they read differently. On anything to do with the fuel delivery systems, they're the same. So if I had low fuel pressure on either system, I would have the same outcome. Or high pressure on either one, I'd have the same outcome. The fuel side of these systems work the same. When I'm reading the air volumes, the trims are going to work differently. And you really got to understand which one that you've got. And we're going to go into this a little bit more as we go through, but I want to make a point of this. So now what I want to do is we want to get back to where we are. And that is, how are we going to figure out the air into each cylinder? So this is one example. Again, please don't get involved in the math. Just get the idea of it. So if I had 5 grams go into the engine, I have 800 RPM, 60 seconds, that's 13.3 revolutions per second. 13.33 revolutions per second divided by 4 intake strokes, 8-cylinder, I'd have 3.33 intake strokes per second. I have 5 grams of air coming in. I would divide those two. I'd have 1.5 grams per cylinder. Do you see how that gets it? You're taking the mass air in, and you're figuring out how much of the mass air really went into each cylinder. And since I only have an intake stroke per cylinder per 2 revolutions, that's how much air can actually flow into the motors during an induction stroke, right? So now if I take 1.5 grams of air per cylinder and I figure a fuel ratio, so let's say we're at idle, I would want stoichiometric, which is basically roughly 14.7 pounds of air to 1 pound of fuel. I'd get a fuel rate of 0.102. I take that by the injector. Now, didn't we know how much that injector gave? It's a 46-pound injector. It gave 0.0483 cc's per millisecond. That would give me an injector on time of 2.11 milliseconds. I need to add a millisecond for injector turn on, right? There's latency in moving the pintle. Since there's latency, it takes time to move it. I would add that time that it's going to take to open and close the injector, 1 millisecond. I add it to the 2. I got 3.11 milliseconds. Pretty basic, right? Let's do the same thing, but a wide open throttle. Now I have 6,000 RPM. 60 seconds, and at 6,000 RPM you're making a stroke in 5 milliseconds, right? Every 5 milliseconds you're making 1 pull. Every 10 milliseconds you're making 1 revolution. So basically we do the same type of math all the way down. We take the 240 grams and we take the 25 intake strokes. I have more intake because we're revving it higher. I would have 9.6 grams of air per cylinder, but now I don't want 14.7, do I? Because I'm wide open. I want to make torque. So we're going to put it at about 13 to 1. Somewhere around 12.5 to 13 to 1 is going to produce the best power on a dyno. So we're going to then have a fuel rate of 0.738. The injector on time didn't change, or the injector fuel delivery didn't change, did it? 0.0483 cc's per millisecond. Wasn't that our given? Didn't change? We have 15.27, add a millisecond, we have 16.27 injector on time. That's really the way we're equating it. And the math is just there as just sort of a guide. And the math can be way more complicated than even these. We're trying to make it simple to get the ideas across. Since the engine control unit is calculating the air into the engine in order to deliver the fuel, the air becomes what's really important. So to diagnose a car, if we figure out what's going on with the air, we can figure out everything about the engine. We're not going to figure out the fuel. We're going to figure out the air, because the air equates into how much fuel went to the motor. We just looked at that, right, with the equation. Volumetric efficiency. Now, volumetric efficiency is just the ability of an engine to pump air. That's it. So the air entering can be used with a very basic mathematical equation. I need to know the liter size of the engine, the barometric pressure, the RPM, and the air temperature. Now I can write an equation. This is basically the equation. N is the volumetric efficiency, max air actual on top, that's this guy, max air theoretical, I divide those in and I can get this guy. Or I can take max air actual, divide it by air density, temperature, displacement of the engine, the speed of the engine, and dividing it by how many pulls I have, right? Got to divide it in half. That gets me the VE. This was first talked about in this culture by Mark Warren in 2003. This technique for VE was used among tuners in the late 90s. So you really start to see VE equations come into our industry, and it came in from the calibration side. In other words, calibrators, you put a cam in your engine, don't you want to know how much air you got pumped? What is my gain? I had X amount, I had 200 grams a second, now I did this cam and heads and pipe and I got 250 grams. That's quantifiable to tell me how much more air my engine pumped. So being able to find this was something the tuners were really interested in. So you can get VE calculators online. You can go and you can Google them, and there's VE equations, and there's all kinds of things that we can use. The idea is what you need to know. You can take your scan tool, you need to take whatever scan tool you got, and you need to program it to make a movie. If your scan tool won't take a movie, get into the new century, guys. Go buy one that can take a movie. Because you really need one that can take a movie. You're going to take certain PIDs, only pick the PIDs you got to have. This is true with whatever system you're working on. You realize that in a communication bus, every time the scan tool goes to the bus, it has to ask the question. That means there's time involved in getting the data back to you. The more PIDs that you have selected, the longer it takes for the loop read speed to get back. So whenever you want to use a scan tool and you want it to be effective, you want the fewest PIDs that you can have. So if you've got 8 or 10 or 20 PIDs picked, realize that the bus data that you're getting back is going to slow down exponentially. Every time you add PIDs, it's going to be taking longer and longer and longer to get back to the beginning to ask. So you could miss a lot of data in between. The key here is whenever you're looking for something quickly, only have the PIDs that you're looking for. Don't have a bunch of extra ones. The scan tool will move way faster. So what if you do this and you go get your calculator and you make a movie, or you use our scan tool, or however you're going to do this? What do you expect? What's the volumetric efficiency, right? Isn't that the whole question? What is this really going to gain me, and how do I know what it is? Well, volumetric efficiency is the engine swept volume. That's the bore by the stroke by the number of cylinders. That's pretty easy, right? Then we would just say how fast it's turning. The more times I rotate the motor, the more times the piston went up and down, and divide it by the intake strokes. That would give me 100% VE. So if I could fill the swept volume of the cylinder, bore by stroke, 100%, that would be 100% VE. But we have other factors that are involved here. It's not quite that simple, so let's look at some of this. Air density. So from minus 40 degrees to 104 degrees, I have a 35% difference in the cubic feet of air. That means that the air temperature alone would have to be equated in any air equation, or you would be trimming 35%. And that doesn't even go into Phoenix where it gets to 115 or 120 degrees, right? We're only at 104. So this could even be a bigger number. But somewhere I've got to equate for this. I've got to know how hot the air or how cold the air is in order to figure out the volume that contains in each cubic feet of air. Barometric pressure. So if I went from sea level to 10,000 feet, it would be a 39% difference. So again, what are we going to trim 39% and 35%? Pretty soon we're going to have so much trim we can't even fix it. These have to be part of the model. These have to be part of the base equations, so we are compensating for these great variants. These are very large in their changes on what they're going to do to the air. So we've got to know what these are. We're going to equate these into the equation. Now the other thing that needs to be done is in engine design, cam function, intake manifold, intake port, intake valve size, combustion geometry, valve size, exhaust port, exhaust pipe. We all have changes in how much air we can pump when we start to change these things. We all know that. We're racers, right? Most of us have built some kind of racing motor. We slap a cam in it, heads, pipes, an intake, and we go and we can burn the tires. Well, the reason you can burn the tires so much better is we're adding more air. It's always about the air. If I hot rod an engine, I'm hot rodding it so it breathes more air. The more air it breathes, I can add additional fuel, and that additional fuel can be turned in. You know, chemical potential is fuel, right? And we're going to take chemical potential and we're going to turn it into thermal energy. The thermal energy is going to heat the working fluid, the nitrogen. 79% of our atmosphere is nitrogen. That's in the cylinder. The Oxygen, which is 21%, has chemistry that goes together with the fuel, the hydrocarbons, to make CO2 and water. The nitrogen is unaffected in the burn. So the nitrogen becomes the working fluid. We're heating the working fluid, and during the expansion of heating that, it pushes down on the piston. Piston diameters start to amplify the pressures that can be made in the engine. Most naturally aspirated engines, the volumetric efficiency is basically 86 to 89, and the high performance engines are 93 to 99. Now this isn't a true efficiency. Volumetric efficiency can be more than 100%. You could have 120 or 30 or 200 if you boost it, right? If you put a turbo or a supercharger, I could have 300%. So a true efficiency could only be 100%. This is not a true efficiency, so we can actually go above 100, and some of the on-highway cars that you'll see actually do have more than 100%, but even the BMWs and Mercedes are somewhere about 96 usually. Those are real common numbers in reality. You can get more, but they usually don't, because we have other attributes such as fuel consumption and emission pollutants to deal with. So we've got these VEs. So we got two different methods. We can directly measure it, or we can indirectly measure it, one being a direct method with a mass airflow. One indirect method is manifold absolute pressure, or a MAP sensor. By either one, the idea is I'm going to calculate the volumetric efficiency. We've talked about volumetric efficiency. It's basically how much the engine can pump in air quantity. I'm going to, now what I want to do is, how do I actually use it? What am I going to do with this? So I figured it out. What does that do for me? Well, let's see what that does for you. The idea is this yellow trace is what's actually being reported. That is the mass sensor. So when you make your movie, you're going to pick the mass sensor, right? And you're going to plot how many grams, and you're going to pick your RPM. Now that I know RPM, and I know the mass error reading, I'm going to get this, and now I'm going to compare it against theoretical error. Theoretical error is that equation we just looked at, right? The VE equation. But you have to have a multiplier to change it from 100%. So these engines aren't going to run 100%, so you'd figure the VE, multiply it by 86 or 89 for most cars. That's going to make a less number, right? Not as much air, less air, and that would give me what I'm expecting. So you could go out and you would make a movie, and you're going to compare it from point to point, and you need to do a few points so you can see over your engine dynamic working load if it stays the same as the engine goes up and down. That's more complicated. So we're not going to do all the equations and all of that. We're going to let a machine do it. I just need to get the idea out. The machine is just a scan tool. It's a real basic scan tool, but really this starts to become drivability, right? To do this. So it's really a drivability tool. Don't fool yourself. You can do this all with your own tools, right? The biggest idea is you got to do it. If you don't figure this stuff out, you're hurting yourself, because this works like it's magic. I'm going to show you magic before we're done today. So the idea is, the yellow trace is actual, the red is theoretical. What we're interested in is the difference between how much we think the engine could produce in pumping capability against what the actual pumping capability from the mass sensor is, right? And if the mass sensor is incorrect, well, that doesn't mean that's actual pumping ability, right? That means that that's what the computer was given as a voltage reading that was converted by a chart, a transfer function table, into gram weight. So if we don't give it the right reading, we don't get the right gram weight. So when I say actual, I want to be very careful with what I say there. Does everyone see that? That's a reading from the mass air sensor. It may be right or it may be wrong. We're going to figure out how we can figure this out. We're going to see this. The engine control module is weighting the air and controlling the fuel. So basically, this is a feed-forward system. Now this is a really, really important thing. You really got to get this. All systems, I don't care what it is, whether it's direct injection, whether it's TBI, whether it's port injection, we figure the weight of air first, and then we deliver the weight of fuel to it. That is fed forward. That means that there's no correction value here. I figure the weight of air. Does everyone got that? How much air went into what? Each cylinder. It isn't how much came in the whole motor, it's how much went into each cylinder. Once I know the weight in each cylinder, I can deliver the weight of fuel to each cylinder, and now I can control the air-fuel ratio correctly. What am I trying to target? Stoichiometric. We'll talk a little about that. It is a feed-forward equation. That's why in the early Volkswagens, if you guys worked on them like I did, anything takes the system down. It's all fed forward. There's no correction. If you have a big factor that takes the equation out, it runs really bad. Okay, how many cars do you guys work on today that have a light on and there's something wrong and you can't even feel it? That's a whole lot of the cars I work on, right? The systems are so good at correcting this stuff, you can't feel the problem. Or I divert to another system. Then we talked about two systems, mass air and direct measurement with a mass air flow sensor, or an indirect with a manifold absolute pressure. What about alpha N? Alpha N is an equation that figures the throttle area. So the throttle effective area is what will be figured. So if I have a speed density system and I lose the speed density system, don't I still have to equate the air to control the engine? It would go back to alpha N. It uses the TPS, the throttle position sensor, and it knows an equation that they've mapped in there that knows how much air is going to be by the throttle effective area, where the throttle is, and it can calculate how much air it is. Early programming systems, like Toltec, that's what they used to use. That was what we hot-rodded engines with. I put those systems on, and you would calibrate the entire engine off the TPS. It's alpha N. It's another way to do it. But you always got to figure that if I lose my mass sensor, I can divert to map if it's there, right? And can I do the speed density equation and still figure the air? Couldn't I go back if I lose both of those and I can figure out the throttle effective area? There's always a background for engineers. They want to predict the outcome. The most important thing when you engineer something is to know a predictable outcome. If I lose the mass sensor, I'm not going to look at it anymore. I'm going to do another equation to figure the weight, quantity of air so I can control the system. If I can't do that, I can't run the engine. It's that simple. You got to figure the air out. So if we figure the air out and we deliver the fuel, now I need to be able to modify it so if I had a problem, I can fix it. My mass air sensor got dirty. So it underread the air. I got to correct it or I'm going to have a lean running engine that could burn valves, tip in hesitations, low power, all kinds of bad things for engineering. The one thing I don't want to do is be an engineer that lets it run lean and I burn the exhaust valves and it comes back. And I got to build the motor under my manufacturer warranty. So we want to control these things. So one way to do this is going to be to use an oxygen sensor. What I want to do is I want to weigh the correct air to the correct fuel. Now, we all have been taught that 14.68 pounds of air to or pounds of fuel to air, 14.68 to 1 pound of fuel, air to fuel, is going to be stoichiometric. But what that really means is that's on pure isooctane. So an engineer takes pure isooctane, one specific species of hydrocarbons, and we put that into the motor, and that's what that target is. When you go to the gas station, that ain't what you get. You get a blend of all different kinds of stuff. So this is really a moving target that's going to move somewhere from about 14.56 to about 14.73. That target moves. And if I add alcohol to this factor, it's going to change it even more. I can get down to 14.2 with alcohol mixtures. And if I ran pure alcohol, I would be down to 8-to-1. Now 8-to-1 to all of us seems like that's really rich, right? 8-to-1, that's stoichiometric on alcohols. So stoichiometric means that I have the right weight of fuel and the right weight of air to where when I chemically put these together and I have a chemical reaction, no two of the prior chemistries are still present. In other words, if I had the air, what am I interested in the air? We already said that the nitrogen in the air is working fluid. I'm not going to react with it. Oxygen, right? So the 21% of the atmosphere that's oxygen is what I'm interested in. And then I'm interested in the fuel. And I'm going to react these two. Well, if I take oxygen and I take hydrocarbons and I break the hydrocarbon chains and I have hydrogen, and H1s will break apart, but as soon as I have an H1, an H2 will connect. Hydrogen will never stay in a state of H1. Hydrogen will always go to a state of H2. So if I have H2 and I cracked an O2, right, I have diatomic oxygen, two oxygens linked together, and I broke one, and now I have an O, and I put it to an H2O, water. Right? Every gallon of gasoline that's burned in an internal combustion engine produces 1 pound of water. Chemically. Has to. Because that's what it does. And when I take the carbon and I broke the H's off of the carbon, I have a C, right? A carbon. And I have O2, and I put the O2 on a C, I have CO2. So I make CO2 and water. That's the chemical reaction that's occurring in the engine. And the chemical potential is really put into thermal energy, right? As I burn it, it gets hot, heats the working fluid, turns the thermal energy into kinetic energy that pushes down on the piston, which turns the crank. So we have different energy sources here. But the idea is, when I have equal amounts, I will no longer have any oxygen, and I'll no longer have any hydrocarbons. In a perfect stoichiometric engine, does that make sense to everyone? All the O2 got changed into what? Water and CO2, and the hydrocarbons broke apart, and all the carbons went to an O2, and the H's went to H2O. Now that's perfect, but in an engine that's not really going to happen, is it? We got piston crevices around the rings, and we got valve crevices, and there's always hydrocarbons that get into these crevices that cannot be burned. So in the real world, what? We need a catalytic converter to further burn the stuff that the flame couldn't get to. So stoichiometric might not be the best place to operate the engine on. Stoichiometric's the best thing for the cat, to keep him alive. This entire fuel system is to keep the cat alive. That's really what fuel injection and all this fancy stuff is. And in the process of cleaning up tailpipe emissions, I've got to be able to make an adequate amount of power for the individual to purchase the car. And I've got to be able to give you a CAFE reading that passes where I don't pay penalties. So the engineers are under a huge load. But stoichiometric is really a moving target. That's really what I want you to start to think about. We don't burn pure isooctane. We get a blend of stuff. And you realize that the different fuels around the world, the crudes, can't even make. If you take North Sea crude, you cannot make a fuel that will burn in a gasoline engine. You've got to mix it with Arabian oil or with the Gulf of Mexico oil. So there's different species of hydrocarbons, and it's very specific to build gasoline. It's not just something, we take it as a granite thing, and it's really not. It's more complicated. So what we're going to do is we're going to use an oxygen sensor, a wide range air fuel sensor, to sense this ratio. Now this balance beam that's right here is going to become the oxygen sensor. I'm going to balance the oxygen with the fuel so I have the right quantities that once I react this chemically, neither of the prior chemicals exist. I'm going to get the right ratio so when I react them, I have neither of the prior chemicals and they've been turned into a lower energy substance. Hydrocarbons is high chemical potential. When I convert it, it goes to a low chemical and it releases the energy, which is thermal. The idea is if I've got an oxygen sensor and I've got a lot of air, that would be a lean mixture. If I have a lot of fuel, this would be a rich mixture. So whether I'm lean or rich is going to be the determination on what? Fuel to air weight. And this weight is idealistic to be where I react all of it, where it doesn't go into the converter, right? And burn my converter up. At high loads, what's high load? Above 70% throttle opening, almost all manufacturers assume that that's wide open throttle. Because if you think about the throttle blade going from a closed position at idle to wide open, that's a 90-degree swing, right? Well, if I go 70%, isn't that almost open, like the throttle blade has very little resistance? So when you're looking at programming, 70% throttle is targeting wide open. What is the driver asking for? Power. The driver wants to make power. I want to pass somebody. Am I going to pass somebody? It's 14.7 to 1? No, I want to go rich. I want to go 12.5, 13 to 1, right? Now the cat will stay alive because the volume of air moving through the cat helps cool it. So I don't got to worry about the cat as long as I'm under high loads with high air going through. Where I melt cats is at low load in the wrong condition and I'm putting fuel into the cat. It melts it because you don't have anything to cool it. So we really need to worry about this. Now we're going to talk about a 4-wire oxygen sensor. In a 4-wire oxygen sensor, we all learned that if I have 0.45, that anything above that is rich and anything below that is lean. That was what I was taught, but that is not correct. Anything above 0.8 volts is rich, and anything below 0.2 volts is lean. So I got to be below 0.2 or above 0.8. Everything else is in this range. Do you see how this moves straight down? So I've got a curve, and then I go straight down, and then I got a curve. So about 2 volts, everything below this is lean, and everything above this is rich. That means that what's this in-between state that we watch fuel control in, which is 0.2 to 0.8, is what? Stoichiometric. That means the chemical reaction is going to fully take care of the burn, right? Right weights, good burn. What's good burn? Tailpipe emissions. This is always about tailpipe emissions, right? For manufacturers. So what I want to do is I want to cycle the O2 in this range. Because if I'm cycling in that range, what is it? Stoichiometric. It's the right chemistry. So I use this as a switch if I'm an engineer. I just make sure that I keep switching within this range and I know that I'm stoichiometric, right? I got to be above 0.8 or below 0.2 to be lean or rich. The engine control uses this and it's going to set my injector on time. So I'm going to cycle the injector on time by the O2 sensor. And that's going to be a feedback, and we're going to look at this. Short term is what's going to set this. The ECM calculates the air weight and delivers the fuel. We've learned this. This is a feed-forward system, guys. I don't care what kind of fuel injection you have. It weighs the air, and it delivers the fuel. Now, there is some different variants on that when I say that. The variants are, what would that be? Well, we got drive-by-wire now, right? So if I got drive-by-wire, I don't necessarily have to dictate this. Because in the old days, I had a Bowden cable connected to the throttle. I stepped on the throttle opened, and I had to deliver the right amount of fuel to cure any kind of tip-in hesitation or lean effects. I want it to run right? Now if I'm controlling the air going into the motor, I could actually look at driver intent, where the driver's pedal is, and then I could predict what the torque output from the engine needs to be. Wouldn't that be a set amount of fuel weight? So if I had that set amount of fuel weight, I could go and I could look at how much throttle I had to open it up to let X amount of air, and then I'd mix X amount of fuel. I would figure the fuel weight first, and then I would make the air right for the fuel, and that gives me the torque. That's how many of the new systems are working. It actually gets you better fuel economy when you do that. Feedback. If I feed forward, I figure the air, I deliver the fuel. Feedback. I look at what I did. In the old days, they had no way to look at what they did. They just did fed forward, so if anything went wrong, the car would barely run. Now we got a feedback. The feedback is a wide-range air fuel sensor or a zirconium oxide sensor or a titanium oxide sensor. There's many different types of this, but I need to be able to equate the air-to-fuel ratio in the exhaust. What did I do upstream? I'm going to check it in the exhaust. This is very much like an oven. if I take an oven and I set the heat at 350 degrees, the burner is going to come on, heating the interior of the oven up. The oven is going to have a temperature sensor in it. Now, the temperature sensor only reads what? The temperature within that oven. Now, I'm going to go up, and I'm going to go from 345 to 355. Then I'm going to go back down to 345, and when I hit this target, the burner is going to come back on, or the element, and then I'm going to get hot, and I'm going to go to 355, shut it off, and I'm going to cycle. So this is a redundant cycle system, and these are very accurate. They can hold the percentage within 2%. So that's really good for an engineer. If we look at the way that this would work, I turn the electric element on, heating it up, I hit a target, I shut it off. I come back down. I hit a target, I go up. What I'm really trying to maintain is what? The center? At 350, this is very much like the way a fuel control system is going to be. In this is actually a scan tool that recorded a live running engine. The yellow is the fuel trim, and the blue is the oxygen sensor. Notice that the oxygen sensor, when the oxygen sensor goes lean, the short-term fuel trim does what? Increases. When the O2 sensor goes high, the fuel trim does what? Decreases. Do you notice how these are exactly in opposition to each other? The fuel trim is who's controlling the oxygen sensor to move back and forth. Short-term trim is directly dictating what happens in that engine. So as the O2 sensor goes down, short-term is trying to take care of it and drive it high. Notice the plane of voltage that this switching occurs at is about 0.45, right? Now, what really happened in this is the engineer told us something. They said at 0.45, if I don't try to control the fuel mixture, I will be rich. I'm going to overshoot it, right? And if I don't try to take care of it when it goes down and I try to add fuel trim, right, to the ramp, so when the O2 goes high, I got to try to control it. When it goes low, I got to try to control it. If I don't take control by 0.45, I will be rich or I will be lean. It doesn't mean that that's rich and lean. You got to be above what? 0.8 to be rich and 0.2 to be lean. Everything in between is what? The sensor can only read stoichiometric. You might see that as a voltage varying, but that doesn't mean that that's not stoichiometric. That's what it really is, if the oxygen sensor is in calibration. The fuel trim is the control of the feedback system. If anything's incorrect, if anything is wrong with the feed-forward system, the feedback has to correct it. So the fuel trim is a control of the feedback system. What I'm going to do is I'm going to do a feed forward, weigh the air, deliver the fuel, and then the oxygen sensor is going to weigh it. And the weight of that is just like the temperature sensor in the oven. It can't really do anything besides report it, right? Who takes care of actually correcting it? Short-term fuel trim. So the trim is who's really trying to balance the scale. And I'm always trying to keep the scale balanced, and that's going to be trim. So let's do a real quick example, 8-cylinder at idle. The total airflow is 5 grams per second. How big's my motor? 5 liters. Hot, unloaded, idle. Hot, unloaded, idle. Liter size of the engine measures gram weight. If I have a 2-liter engine, hot, unloaded, idle, that means not in gear. That means no headlights on, no air conditioning on, and if your daytime driving lights are on, it's fine. But we don't want to put an additional load on the engine. You got to always remember, during an idle period, the idle is just enough to overcome the parasitic losses of the motor, right? I have frictional losses, I have viscometric losses, pumping losses from making oil pressure. These losses, all I'm trying to do is to overcome them. That's why I need a power steering switch. So when I turn the power steering and I start to load it, I've got to give it more air so I can increase the fuel delivery to keep it running, or that's why if I put the air conditioning on, I need more air going in so I can give more fuel to keep it alive. At idle, I'm just trying to overcome the parasitic loss of the motor to minimize fuel usage. So what we've got is hot unloaded idle matches the liter size, right? Hot unloaded idle matches what? The liter size of the motor. Dude, this is one of the best things that I'm going to teach you, because this is a huge gain when you're looking at fuel trim problems at idle. What cars don't abide by this? Suzuki, Hyundai, and Kia. You better be really careful with those. Those guys, I know, some of them read right and some of them don't. Pretty much everybody else abides by this rule of thumb. You know, there's always exceptions, but this is a really, really good rule of thumb. So I've got 5 grams, 800 RPM divided by 60, 13.33 revolutions per second, 4 strokes. 5 grams divided by the strokes per second is 1.5 grams per cylinder. Again, we got to figure out the cylinder weight. I'm going to target my air weight. I'm going to figure my injector that we had. That's 2.11. Okay, so that's 3.11. Now, let's look at a mass sensor that misread. I've got 8 cylinders at idle. Total airflow going in is 4 grams. What should it be? 5. So if I had 4 grams on an engine that's at hot idle, what do you already know? Something's wrong. It doesn't mean that it's wrong, but it means it's waving its hand and it's telling me to come look. It's like one of those DTCs that we looked at. It doesn't mean that that's what's wrong, does it? Do diagnostic trouble codes tell you that that's what's wrong? It doesn't. You know what it tells me? Is he's got his hand waving, and it says, look at me, pay attention, something's wrong. It doesn't mean that that's what's wrong. So if I got a low air rate, I've got to look at a couple of other things to know if it's right or wrong. We're going to look at that. We need to look at the trim to figure it out. So basically, if I've got 4 grams by this, I come down, I get a 2.67 millisecond of on time. What did I need? 211. I add 1 millisecond for my injector turn on time, the delay. That's latency, or the delay of opening. So I need 311, but I don't have that, do I? So to fix that number, I've got to take fuel trim and I multiply 16.5%. 16.5% by 2.67 is 0.44. That takes me back to the 311 I need. Do you see how fuel trim is working? Whose fuel trim? What am I doing with trim? It multiplies the air. This is not about fuel. This is about air. We call it fuel trim, but we did not do that. We increased what? The volume of air. And if I have more air going into the motor, what do I got to have? More fuel. If I decrease the volume of air, what do I got to do for less fuel? Decrease the on time. Fuel trim is a multiplier to the base air equation. I'm multiplying the air to compensate for a problem. Does everyone understand that? This is not about the fuel, it's about the air, guys, and when you look at the math, you can really start to see it. This is a VE table. So this would be the load by the RPM. And this is another thing like fuel mapping. They show you these fancy tables. You know the mountains? And they say, look at this wicked timing table we got for our ignition. We're advanced. We're Bosch, and we can program ignition, right? This is how it really works. You take that table, that is a 3-dimensional table. The mountains come out of that 3-dimensional table. This is not anything fancy. This is a basic chart. I fill in a chart like this. This chart is actually a 3-dimensional chart. It is very powerful. Now that we have an idea of how this injection is working, that it has to do with the air, how am I going to use this in my shop? Because if I came here and I'm just up here talking, then I've wasted all of our time. And that's the most important thing to each of every one of you have is your time. How are we going to use it? I got to fix cars, and I got to fix cars Monday morning in your shop. If I failed that, I have failed in coming here. So now that we understand this, what I want to do is we're going to give you a formula to fix these cars. All these drivability cars, quickly and accurately. We're going to start with a 2003 Kia Sorento. Here's my car. I have a DTC, lean airflow. This car has had 2 rebuilt sensors on it. So how many sensors is that really? 3, because it had the original one on that came in, right? So we've had a few sensors put on this car. Okay, I've got all the oxygen sensors replaced, and we've replaced the intake manifold gaskets. Because it must be leaking because I did all this other stuff and it didn't fix it. This is how we work on cars. Right here. I'm going to show you this over and over. I go to shops. We've got to be better than this, guys. We are professionals. And we can execute this as a professional. We don't put parts on, we diagnose cars. How do we do that? Well, here's the Kia. We got a check engine light on. We're going to take our VE readings. We're going to take a scan tool. We're going to get some really basic things. System, bank 1, bank 2, lean. Okay, that's a no-brainer. That's why I'm here, right? When I work on a car, I do not look at DTCs. I look at them, they wave at me, they tell me something. It's just another PID. It's no different than if I looked at the mass airflow rate and I think he's low or he's high for my air rate. That didn't mean that's what's wrong, because I got a low mass air rate. That tells me the mass air sensor's bad. What about a vacuum leak? What about a bad ground or a bad power? What about a cam? What about a plugged exhaust? What about? It means that I've got something over there to look at. DTCs, that's an indicator. A knock sensor. Am I going to get involved in the knock sensor? I am here because the car doesn't run right and we're lean. Focus on the symptom. The only time the DTC it matters to me at all is when it is the symptom. It's an evap code. I can't feel it. It says it's leaking. Then it becomes the symptom. Do you understand that? If I've got something else happening, I deal with that. I deal with symptoms. Always follow the symptom and the data, and you always fix the car. Okay, this is a 3.5 engine, hot unloaded idle. We have 3.63 grams of, is that correct? That would be, but what is this? This is a Kia. I told you guys, man, be scared of Kias and Hyundais, because they could be anywhere on this number right now. They will match the VE because the VE is a calculation based off of swept volume. That is physics, guys. We're going to deal with physics and we fix cars. We deal with our gut feeling and that this car's red and that car was red, so we have the same problem. That's how we don't fix cars. Okay, I don't know about this right now. But you know what? I've got 3.63 and I'm adding 19 on one bank and 17 on another bank right now at idle. Now if this wasn't a Kia, what would I say? It's in the fuel because the air read correctly. Does everyone else's car just about, if the air is right, what did we do? Feed forward? We did feed forward. We weighed the air and we delivered the fuel. So if I weighed the air and it's a 3.5 and I got 3.63, didn't I basically weigh the air correctly so I would have added the right fuel? So what am I thinking? Fuel pressure, right? We need to do something greater than this. We cannot look at fuel trims static in the bay. This is one of the main problems that I see shops make. They get a fuel trim problem and they think they can see it sitting there in idle. You are making a drastic error. You have to run the engine through the dynamic phase. You can't look at idle and say it's good or it's bad. We need to look at the range of performance. We need to make the engine produce power. Does that make sense? That's how I'm going to figure out what's wrong. Okay, one of the things I always do when I go drive the car that's got any kind of a problem, I floor it. When I floor the car, okay, so here's my RPM. The RPM came up. Here's my grams, mass air, and my math. And do you see that this is my bank 1 sensor? Do you see how bank 1 came high? 0.8 volts. If it's at 0.8 volts, it's what? Rich. And if it's at 0.2 volts, it's what? Lean. Very good. So at this point, what do I have? I have rich. That means I did what under full load? Controlled the fuel. If I open the throttle wide open and that O2 falls down, you did not control the fuel. Because under heavy load, the manufacturers, calibration engineers are going to add fuel to make it rich, right? When you go past how much throttle? About 70%. If I'm above 70% throttle, what am I? Rich. Did I stay rich on this car? So what did I do? I was able to control the problem. That means that the fuel trim could overcome whatever failure this car has. Fuel trim is fixing it. Does that make sense to everyone? Very good. This is what you got to do. You got to be able to check the trims dynamically in loaded conditions. This is a dynamic table. If we look at this, we have the throttle position on one chart and RPM on another. These charts are very helpful. If you don't have the chart, you absolutely need to make a movie of this. Put your scan tool and take your RPM and take your throttle position sensor as I open it and my trims. That means long and short, guys. We always add long and short together. Because if I was adding 20% long term and I'm taking away minus 20% short term, what's your trim? 0. Do you have a problem? No. Always I'm worried about total trims, long and short. I always want to look at long term to see if it's got overall issues, but the total trim is what I'm really interested in. If you're going to take a movie, you need to graph this stuff so you can go back and you can see dynamically where your throttle was, where your RPM is, and what your trim is doing at that position. Does that make sense? You can do this with your scan tool. These charts just make it so easy. It's quick, it's easy, it's accurate. Okay, no, we don't do VE until we have over 50% throttle opening. So really, to do volumetric efficiency, you want to be what? Wide open. Pedal on the floor, throttle wide open. You can be as low as 50% and still have some accuracy. If you're below 50%, you start to get into other things other than just the total ability of the engine to control the pumping ability, right? In other words, where are your cams? If I phase them, how am I phasing them? When I start to get in lower positions, we actually do what's referred to as internal EGR. Cam phasing, I put a lot of overlap in the cams. It makes an EGR. You want to know why your EGR valve isn't there? You know, an EGR, originally in the 60s, EGR was put on mandated by the state of California to reduce what? NOx? And NOx has a problem when it gets into the atmosphere to become ozone. Same with hydrocarbons. So pure hydrocarbons and NOx get into the atmosphere and they have a photochemical change from the sun. And that makes ozone, and ozone is smog. Smog is what? An acronym for smoke and fog, which means smog. So smog is ozone, and ozone is an irritant to human eye, skin, it's bad. So we want to control the ozone. To be able to control the ozone, I got to control the NOx. To get rid of NOx, NOx is created under high pressure, very rapid pressures, or very high temperatures. So if I have shock waves in the chamber, like pre-ignition, I make a lot of NOx. Or if I have very high temperatures above 2,500 degrees. Now, 2,500 degrees is a lot, but that is the temperature it takes in order to put nitrogen and combine it with what? Oxygen, because isn't that what NOx is? Nitrogen and oxygen. It takes energy to put molecules together or to break them apart. In this case, we're going to use thermal energy. NOx was put forth, we're going to control it. You know how when you take a cutting torch, and I'm cutting and I want to make it less hot, what do? Take oxygen away? And if I take oxygen away, my torch isn't as hot, and I can't cut the same big thick piece of steel anymore, right? I want more oxygen, and more oxygen refers to more thermal energy, which equates and I can cut it easier. Does everyone get that? So if I took inert gas that had already burned, and I put it back in and displaced the air in the intake manifold, didn't I take oxygen away? What was the base effect? I cooled the chamber down so I don't get it above 2,500 degrees. Now, with modern motors, I no longer need an EGR to control that. I can control it with the combustion chamber geometry. How the chamber is designed will control NOx. So the NOx production is controlled by design rather than EGR. EGR is used on modern cars, whether I have a valve or whether I do it internal, to reduce my pumping loss. When you're at idle and you open your EGR wide open, what happens to your vacuum? Goes down, right? Because I displaced the vacuum with the exhaust gas. So if it goes down, I don't have as much vacuum. Well, when the piston's moving down, that's a lot of energy that's parasitic loss to the engine. You lose mileage, right? Because I'm fighting myself. Every time I pull the piston down, I'm pulling against that vacuum that's in there. Does that make sense? Well, that loses energy. And everything right now is about how to make engines go further with less gas, right? So the idea is I want to get rid of the vacuum. To get rid of the vacuum, if I open an EGR up, what happens to my vacuum? It drops. What happens to my parasitic loss? I do better with it, right? So whether I've got an EGR on a modern car or I internal EGR by moving the cams and getting heavy overlaps between the two valves, I'm really doing that for what? Not to lower the temperature anymore, but to lower my pumping losses from the vacuum cycle pulling the piston down. Does that make sense to everyone? Okay, so basically, let's get back to what we're doing here. We want to do a dynamic test. We need the throttle basically 50% open to do a volumetric efficiency test. We have our fuel trims loaded over load against RPM. We'll go up to about 40% throttle, 40%. Do you see how I'm 24%? Do you see how up here I'm 36%? I'm 22%, I'm 36%. Both banks are basically doing the same thing, but do you see how when I'm going from is 24, 25, 25, 24, 28, 34, 36? I'm going from a lower trim to a higher trim. How your trims change under load is absolutely critical to diagnose the car. You've got to know whether these are linear or whether they're curved. We're going to look at linear. Linear means from one position to another and I draw a straight line. Does that make sense to everyone? A curve is where I'm curving up. It's not linear, it's a curve. How these trims are going to lie tells me what I want to go look at, where my problem is. In this case, I'm adding more fuel under more load, aren't I? Now, what do we know right now? We know we're lean and we're adding fuel to get my right air-fuel mixture. Does that make sense to everyone? I'm adding fuel to what? Target an air-fuel ratio. In order to do that, I'm going from low to high, but we don't know why. We just know we're adding, right? We need one more piece, volumetric efficiency. When you put these two things together, pure magic happens. This is just magic, guys, and I'm going to prove this. What happens with this motor? Do you see how this motor went to 95 grams of air? Well, theoretical air says I should be at 130 grams. So if I only read the air going into the motor and I read 95% and I needed to take 95 to where theoretical is, if I took 95 by 37%, I'd have 35.15 more grams. Add that gram, the percentage here, to my equation, and do you see how I'd have 130 grams where theoretical went? This scale is the difference between actual red air, this is from the mass air, this is what the mass air is reporting as air, right? What happened to the air? What did it have to do to get red? The mass air produced a voltage. The voltage is read by an analog to digital converter. The converter is set to a binary code set. The binary code is read by the microprocessor, and that voltage equates to a chart that tells it how much air there is in there. I want to stress this chart. Every system has to have a way to transfer a voltage to something the computer can use. It's just the way you've got to program it. Does that make sense to everyone? Okay, so in this case, I have 95 grams. I need 130. Now, to make up for this, do you see how I have 25 to 37? This is the difference from actual to theoretical, 25 to 37. My trim's 24 to 36. Do you see that the trim is modifying what? The base air equation. Trim changes the air, not the fuel. If I tell it it's got more air, what do I got to do? Turn the injector on for a longer period of time, and the injection on time gives me what? More fuel. Does that make sense to everyone? If there's any questions, please ask me. Do you see how the trim over the load, the dynamic movement of the motor under load, matches the VE? What do you know? Your trim is caused by the air reading. That's what you know. The trim is caused by the air reading. If the air reads right and the trim is wrong, it's on the fuel delivery side. This test divides the two halves of the motor. It divides it between the feed forward, the air read and fuel delivery, and the delivery side. Delivery is the injectors, the on time for the injectors, the feedback system. There's a few things involved here, but we're going to get to that. But first we want to understand the air. Does everybody see how the air directly matches the trim? That means that the air is your problem. This isn't a fuel pump. This isn't the injectors. That's what this is telling you. Do you realize that we made this test in 3 minutes? This is 3 minutes of my data. Didn't I have to drive the car anyway to see what it was doing? Do a scan tool. Go around the block. You'll know what's wrong with the car before you get back. So what do I know I've got to do? I've got to check the mass airflow sensor, right? So I want to show you something. We're going to take a scope, because the only way you can do this is a scope. We're going to check the powers and the grounds at the mass air sensor. This sensor works off of current. Didn't we say that? That the current is proportional to the airflow on the hot wire? The hot wire is going to make a signal on a scope like this. I have my power. Do you see how my power is good? And do you see how my ground? So I have a good ground and a good power. Before I put any mass sensor on this car, or any sensor on a car, I have to power it and I have to ground it. And if I don't check those, I'm making a mistake, because I might put something on there that didn't fix the car because it's a voltage drop. We saw that a lot with Mr. Colonna's presentation. He showed you all kinds of voltage drop problems that would cause erratic drivability, or in his case, shifting issues. The idea is powers and grounds become absolutely essential. We absolutely have to test these, and we got to know they're good. So before I'm going to put the mass sensor on there anyway, I got to do this test, right? Let's put a scope on it. I'm going to show you a really good trick. This works really well for me. I've been doing this for 20 years, this trick. The idea is, I'm going to have it idling, and I'm going to snap the throttle wide open. I'm going to let it go back, and I'm going to snap the throttle wide open. This point right here and this point right here is what I'm really interested in. Think about what happened here. The throttle blade is closed. The induction system is under a heavy negative pressure, right? Vacuum. Atmosphere is a high pressure, in the intake is a low pressure. High pressure always goes to a low pressure. If I take the restriction away and I snap the throttle open, the atmosphere rushes in to fill that low pressure area. At this point, I almost have the highest VE I can have on a motor. I can get it higher than this, but this is really a good test because I'm loading the sensor, right? I'm actually checking it dynamically. Now, what I want to do is I'm going to take this guy and I'm going to zoom in on this. So we're going to zoom this with the scope. Now, do you see how I came up to 3.47 volts on the peak? So what I'm interested in this rise right here, how high I went. 3.7 volts in height. Now, an analog to digital converter on these is a 10-bit resolution. Most of the sensors for analog is 8-bit. That means I look at them 256 points of resolution. I need more resolution because we're looking at such small millivolts from these sensors. I'm going to demonstrate this in just a second. But one thing I know is I want the most change that I can have. Think about this. I've got an engine, and through its entire load, I'm going to go from somewhere about 1 to 1.5 volts at idle, right, roughly, depending on the system and the mass air sensor. And then I'm going to run it up to another voltage. Now, I have basically a 0 to 5 plane, right? So wouldn't I have basically 0 to 5 volts? So the closer I get it to 5 volts, the more resolution I have to break that voltage down into grams per second on my table. Remember the transfer function table? So I want the largest gain for my A to D. I want the sensor to go close to 4 or 5 volts as a general rule. That just makes sense, doesn't it? Let's make sense out of this stuff. Let's think about it like engineers, because each one of you is a scientist. Every day in your laboratory, your bay, don't you make conclusions? Don't you come up with a theory? Isn't that what science does? The difference between scientists and most shops is shops never prove their theory. They just put the part on it. What I want to start to do is prove the theory with science. Do you understand? That's how we fix cars. Now, I know an analog to digital converter is going to change this voltage into a transfer for actual grams. I also know that I want the greatest voltage change because I can do more with my program. If I've got 1 volt and all I change is 1 volt over the entire load of this engine, so this engine is going to go from 5 grams a second to 300 grams a second over 1 volt. Do you see that the resolution in that volt would be a very tight chart for me to write? But if I took that same one and I went from 1 volts to 4.5 or 5 volts, wouldn't I have a much wider voltage to program the table with? Doesn't that make sense? That's what we're going to do. So engineers are interested in using the most capability. The most capability is to make the signal higher. Most mass sensors will go higher than 3.5 volts. That's what I'm going to tell you. How do we know how this is really going to work? You're going to need to test some known good cars. Yes, sir?
I got to ask that, Bernie, a lot of these sensors are in that 5 volt range. If they want that wider range on a 12 volt system, why don't they use the full 12 volt?
The 12-volt system, if I wanted the entire range, very good question, Peter. Peter's question is, if I want the entire range, wouldn't I go up to 12 volts? 5-volt regulation is pretty much a standard, and I can control the voltage. When I start to get closer to charging system voltage, I can still put a regulator on it, but if I'm at 12 volts and I lose my charging system, and it comes down below my 12-volt level, which I still want the car to run with, which is also a good question. This made me think of something else. Inside the computer, you have another piece of this algorithm that watches voltage. And the battery voltage, or the BTO, the battery on time, right, is going to be based off of voltage. So when I lose my charging system, I want to be able to let the computer continue to run. It comes down from 12, 11, 10, 9, 8. I might not have enough voltage to crank the car over because that would require a huge amount of current, but I would still have enough power to run 5-volt generators, right? A regulator. So if I can come down below 12 volts, now it gives me the ability to, once I've lost my charging system, I have a predictable outcome. Engineers always look for predictable outcomes. So really, I want to start, and I want to come down to 5 volts where I can let it come down. Now, that being said, the battery voltage is read by all the processors because that's one of the things you program. So if I program this unit for battery voltage and I start to drop battery voltage, I start to increase my injector on time because the length of time, the latency it takes to open the pintle becomes longer. Why I'm telling you this, you get a voltage drop on the signal wire, the sense wire, you will have erratic fuel trim problems that you won't figure out. The actual battery voltage is part of the equation. It's like the barrel temperature, the barrel pressure, and the air temperature. I've got to know these because these are variables, right? Always check on your scan tool your voltage PID. If the voltage PID is low, if I come down in voltage, what am I going to do? Increase my injector on time? What does that mean? More trim? I'm going to have to tell it I have more fuel, more air, so I can get more fuel. Does that make sense? But if I got a voltage drop on the wire, did I need that fuel? No. And if I'm overcharging, then I cut back the injector time. So if either the voltage has a drop going to it or the analog to digital converter that's in the processor misreads that voltage, you will have trim issues and you will have injection problems, right? Drivability problems. So thank you so much for the question because it always makes me think. And please ask me questions. But the analog to digital converter is a key component just like the baro is. And that's actually part of the equation that's programmed into these systems. Okay, so basically, I'm snapping the throttle and I got 3.47. Now, I don't got to know all these, but I need the idea. A lot of times, I'm going to go find another car to find the right snap. He's got a rebuilt MAF, and I don't want to do a rebuilt MAF. These rebuilts are a really bad deal for us. And I'll explain why in a minute. But basically, rebuilt has problems. That's what I equate. I told the dude, he's already had two. This is the second one, and he had the original one on there. He no longer has the original one. I had him call the parts house to find out if we could get it back, because I want to get back to where I started. It's gone. I told him, go get a new one. He says, I can't. It's $700. He already released this car to his customer. They've paid for it. This is on this shop. Okay? So he can't go. He already put a rebuilt one on for $200 rather than the factory original, which was $700. Do you see where he is now? He's stuck. I called a junkyard, a salvage yard. Apologize. I do a lot of work with these guys. They had the car. I called him. I told him, do you have a used one? He said, yeah. I told him, go get it. And I went across the street to the tranny shop and I diagnosed a tranny. And then when I was done with the tranny, he had that MAF sensor. So I went over and I put the new one. So this is the rebuilt one and this is a good used one, right? That he got from the salvage yard. I'm going to put the good used MAF on. I'm going to do the same snap test. Do you see how I'm 4 volts now? Did we change something? I know that. Now this is a real quick, dirty test. I want to make sure we understand what I'm doing here. I'm snapping the throttle and I'm looking at a voltage. We're dealing with such small voltages that you can't see some of the problems, but if it's a big problem, this works really well, and I'll demonstrate this a few times during this seminar. So 4.8, that makes sense to me. I've got more resolution. I'm thinking that's right. How would I know how to do this? The VE test is going to prove this, right? I want to do a really quick analogy. The MAF idle, 4 grams. MAF wide open is 130 grams, right? There's a 124 gram difference. The voltage goes from 1.33 to 4.8. These are good sensors now. The difference is 2.75 volts. That's 2,750 millivolts divided by the 124 grams. That's the difference, right? That would mean that I have a 22.17 millivolt per gram. 22 millivolts equals 1 gram. Do you see why you have to have more resolution? A little bit of voltage is a lot of air. So basically, if you had a volt, you would be at 45 grams difference with 1 volt. We're dealing with very small voltages out of these MAFs. Now I put this as inaccurate because MAF sensors do not a linear position. They don't go from idle to wide open and it's a straight line. They're very curved. So towards more than 50% throttle opening, mass airs have very little change. They want most of the change when they engineer the sensor. Most of the change is going to be down at the bottom where you're driving. And the most change will come in at that position. The good one now is 4.09. What size engine do we have? 3.5. What would have I expected on any car besides Kia, Hyundai, and Isuzu? And there's other exceptions. I'm just saying the big exceptions I know. I would expect about 3.6 where we had, right? Since this is a Kia, it's at 4 grams. Now look at your trim. So my long-term trim is still at 13, but that's my gram. Why didn't it change? Because I haven't run the car yet. In other words, to get the trim to change, I've got to run the car in that loaded cell. And it's got to run for a while. I snapped this as soon as I started the car and let it idle down, right? Where's my idle? My idle is at 839. Do you see that? I just want to show you something that's real quick. I'm going to do the VE test. Now, do you see how actual and theoretical mirror each other? They're right on top of each other, and you see the difference here? Did you fix the car? If you just did a VE before and a VE after, you know you fixed the car with the sensor. Does that make sense to everyone? And I don't guess. I don't got to let the car go to see if it's going to come back. I already know that the mass sensor is fixed for sure now. That's the power of VE. The Fuel trims. Now all I did was drive this car around the block. Do you see how I started to change the trims back to where their position is? Now in order to change the trim, in each cell you have to put the car in that load at that RPM, and it has to stay in that cell for significant time enough to retrim it, to bring the trims back into position. Does everyone understand that? You cannot go and drive a car and the trims aren't going to all go right away. The car has to go through its cell structure or the fuel chart, and every time you get into the cells of the chart, it will trim it. Yes, sir?
Does that key have a way of resetting the adaptives?
You do. You can either do a battery reset, which isn't a good idea because you set so many different adaptives, such as transmissions, radios, maybe you need a code, or you can clear them. And on many cars, when you clear the codes, it'll reset these. Personally, I never clear anything till I fix it. Now, we saw the VE, and the VE fixed the car. It changed the VE readings back to what we expect. Is that true? Now, we drove the car around the block. Did the fuel trims move in the direction I expect? So we know the trims aren't stuck, and we know the trims can move back. So now when I take the car back and I clear it for my customer, it's fixed. As long as I see those trims move in the direction I expect, what do I know? The trims can move, the feedback is working, and I fixed the problem. I'm not going to get the car back. That's why I don't clear them yet. Does that make sense to everyone? So now, we're going to go and we're going to take a break, and we're going to try to do a 10-minute break. I have so much to get to, I can't tell you. Please, let's try to be back in about 10 minutes so we can get going on this. Thank you so much. Ladies, gentlemen, we want to get started here again. Okay, I want to go back and I want to cover a couple of things that were key questions during the break. So I want to go back to this very reading. This is the car we've already done, right? This is the Kia. Okay, my trims go from 24 to 36. My VE, my actual sensor is reading 95 grams. But what really is going into the engine, how much air really went into the motor, is 130 grams of air. The mass air is misreading the air. Do you understand that? Really, how much air went into this engine is 130 grams. The mass air sensor is saying that we only have 95 grams of air because it's bad. Now, in order to correct that, I have to multiply using the trim. So if I correct it, do you see how I've got 36% at the top? And do you see how if I put 36%, I would add that much more air to this? So if the computer, if I read 95 grams, and the computer modified this grams by a multiplier, so I multiply it by 35%, I now say I've got 130 grams of air, which is correct. The air-fuel ratio is correct now. Does everybody understand what we did there? The air is actually misread. We really have theoretical air going into the motor, which is 130 grams. The mass air says we have 95 grams. We did a feed-forward equation. We had 95 grams to start with. When I had the 95 grams to start with, that's how much fuel I gave that engine, is for 95 grams. Does that make sense to everyone? Now what are we? We're lean. The feedback system, the oxygen sensor, looks at it and it starts to correct that number. Because we need to tell it it's got more air, so we add more fuel and we keep it stoichiometric. So the idea here is, guys, feed forward and feed back. We got to understand that. We weigh the air first. Whatever that reading is, however much that weight of air is, and that's with a MAP sensor too, right? Manifold absolute pressure. In many of the systems, when you look at Hondas and Chrysler, Dodge, Jeep, they didn't even have mass sensors until late 2000s, right? Well, the idea is what did they do? With the speed density system, didn't they give you grams per second on your scan tool? Because they had to figure how much air weight is going into the engine, or you cannot fuel it. You have to be correct with your air equation so you can fuel it correct. It's always feed forward. It figures the air first, and then it delivers that amount of fuel. If I figured the air at 95 grams and I added enough fuel for 95 grams, but really I have 130 grams, is the car going to run? Very poorly, right? It's going to be lean. It isn't going to run good. To make this car run good and to correct the incorrect MAF sensor, the MAF sensor has drifted its calibration, right? It no longer reads the air right. To correct it, the computer does a feedback now. And with the feedback, it corrected 36%. Isn't that exactly how much we needed to get the air back? You got to start to understand this stuff is about the air. We keep modifying the air to get the right air-to-fuel ratio. Does that make sense to everyone now? His question is, the computer knows that this should be able to get 130? It does not know that. The computer relies 100% on the mass air voltage. It takes the voltage, it looks it up on a transfer function table. Whatever that voltage is on the transfer function table tells me how many grams it's got. That is what is used in the program to deliver the fuel. We're done right there. Now, when I put it in, and I look at it with the O2, I'm lean, right? Now, if I'm lean, I have to add fuel for it to run right? So the feedback function, which is the oxygen sensor or the RAF sensor, he says I'm lean, I add more fuel. How did I add more fuel? I said I had more air. I multiplied the air. I said I had more air. If I have more air, what do I got to do? I turn the injector on for longer? That's why these numbers match each other. You know, I'm not making this stuff up. This is just the data, right? We collected the data and we're showing you this. The data is the fuel trim is what? 24 to 36. Do you see that? That's just the data we collected. What's the fuel, the air? Okay, 25 to 37. Don't those match each other exactly? Because what the fuel trim did is it made me say I have more air, so what? I'm in fuel control. It's trying to always keep it in fuel control, and I'm modifying that number to get calculated load. Uses several things. Calculated load uses two things that aren't desirable for us to be using. Standard air pressure and standard temperature. That means that that equation always has standardization. 70 degrees air at sea level. Well, what happens when I'm at 5,500 feet and it's minus 30? Does that work for me? So calculated load doesn't always work because it has two standard numbers in there. And how big is the number? Well, we saw the air temperature's huge, it changes, right? But it doesn't use that. Calculated load uses two pieces of data that are critical, but they standardize them in it. Now, if you put the mass on and you looked at calculated load and you looked at it again and you add a difference, you could figure it out. What I'm trying to show you is beyond calculated load. This is the next level. This is what the computer is doing. We're doing what the computer did. Does everyone understand that? We're trying to back it back out to where the computer, we're seeing what it did and we're correcting it. Calculated load isn't how they're calculating the load to the motor. How they're calculating the load is looking up the voltage off of the mass air sensor, going to a transfer function table, converting that into grams, then figuring out what delivery rate of fuel. That's what it's doing. That's what we're doing. Do you see how we're trying to get back to what happened to start with? It's way more accurate. Calculated load works great. I'm not knocking it. I'm just saying that there's a better way. If that was my only way, that's what I'd be using, right? But there's a better way. We're trying to show better, quicker, easier. And as we move through this presentation, I believe we can get there. So theoretical air is the swept bore by stroke by RPM temperature, right, divided in half, gives me what the theory at 100%. Now, that theory, we're not going to be at 100%. So for a particular motor, I have to apply a multiplier to the number. The multiplier is what I showed you earlier. Most cars are between 86 and 89, and some of the high-performance engines are 96 to 99. That's why I gave you those numbers. Those are standard numbers. In our scan tool, you pick the engine, and we automatically put the right multiplier for the motor. It makes it way easier, right? Let's be realistic. I'm a flat rate technician, right? The biggest thing that I'm interested in is I'm interested in how fast I can fix the car, not how much like Einstein I am. Do I want to start plugging all these numbers in? I want to drive and have the tool do it for me. I can dig a hole, guys. I can come put a swimming pool in your house. I can dig it with my hands. I could take a shovel, or I could take a backhoe. Take your pick on what tool you want. You'll get the hole dug with any one of them, right? I'm taking the backhoe.